Hello, everyone. Good afternoon, ladies and gentlemen. We are beginning the 14th technical session of CBGRAPI with the subject Neural Networks and Classifiers. In this section, we will have three presenters, three papers, very excellent papers. And the first one is a lightweight 2D pose machine with attention enhancement. So the speaker is Luis Schimmer, and we'll have the questions just after the presentation. So let's start.
A lightweight 2D pose machine with attention enhancement. This project is a collaboration between PUC-Rio and INPA, and it's about real-time human pose estimation. Pose estimation is a challenging problem in computer vision, with many real applications. Usually, the problem to be addressed involves estimating the 2D pose, the anatomical key points or body parts of persons in images or videos. Inferring the pose of multiple people in images presents a unique set of challenges, considering the number of people appearing in different scales, occlusion, and also the runtime complexity tends to grow with the number of people in the image. If we find a way to leverage the performance for this task in real time, it would be hugely beneficial for a large range of applications, such as motion capture, or animation, robotics, understand sign language, and many others. OpenPose presents an evolution of pose machines with a bottom-up approach for pose detection and a huge reduction in computational cost. However, it does not achieve the desired performance in terms of frames per second in real time, considering both versions of its architecture in a limited hardware. Several papers propose real-time approaches considering deep neural networks for pose estimation. However, in most cases they fail when considering runtime performance or do not achieve the precision needed. Also, convolutional pose machines are fully convolutional neural networks, and there is evidence that a key feature behind the success of these methods is over-parameterization. It could help in finding a good local minimum, however, it also leads to the large amount of redundancy. Furthermore, models with a large number of parameters have increased storage and are computationally intensive. So, how to improve performance and maintain accuracy? We propose a new model for real-time pose estimation considering attention modules for convolutional neural networks. We introduce a two-dimensional relative attention mechanism for feature extraction in pose machines, leading to improvements in accuracy. We create a single-shot architecture where both operations to infer key points and part definite fields share the information. Also, for each stage, we use tensor decompositions to not only reduce dimensionality, but also to improve performance. This allows us to factorize each convolutional and drastically reduce the number of parameters in our network. Our experiments show that with this factorized approach, it's possible to achieve state-of-the-art performance in terms of runtime, while we have a small reduction in accuracy. We perform tests in CPU, and as we can see here, our approach has much better performance, considering frames per second, while the original OpenPose is impractical to be used for real-time applications in limited hardware. Running on CPU, our model can achieve almost 50 frames per second. We also perform tests in low-cost GPUs, where we can expect to predict a pose in 35 milliseconds, which is almost in real time.
So, good afternoon, Luis. For the moment, we don't have questions about your paper, neither from YouTube nor and from WOVA. But I'd like to make the first question. What is the really significance and tensor decomposition in this in this paper? So
okay, and using the tensor decomposition, we can decompose each convolutional layer, so we can improve performance of our neural network, so we reduce redundancy. For example, comparing to OpenPose, we have a performance of 9 times better than OpenPose, for example.
Okay. We have another question here from YouTube. What's the intuition behind the different skeleton model using when compared to OpenPose? Also, what's the difference in the accuracy?
Okay. Actually, we use a technique similar to OpenPose to generate the skeleton. For example, we use the part-dependent fields and key point detection, and after we use an assignment problem resolved. So the difference in accuracy, for example, OpenPose in Coco dataset has an accuracy, an average precision of 80%, and we have a precision of 74%. So we have a smaller reduce in precision due this decomposition, for example.
Okay. Claudio Jung is asking, did you try using neural networks pruning schemes such as in EfficientNet?
No, we didn't test this technique.
Okay. There's another question from Thiago Silveira. Does your methods apply frame by frame? If so, how could you explore temporal coherence?
Yes, this method is frame by frame. In another work, we explore the temporal coherence, but in a post-processing step, for example, using the KLT algorithm.
This temporal coherence could improve the results?
Yeah, we believe they could improve the results, but however, we are still exploring this, so we don't have any results to show yet.
Okay. Is there any other question? No. So thank you very much, Luis, for your presentation. And let's go to the second speaker of this section. That is Kelvin Cunha. He will talk about a study on the impact of the main randomization for monocular deep 6DOF pose estimation. So, Kevin, you can continue your presentation.
I'm Kelvin, and I will show you the highlights of the work is study on the impact of the main randomization from monocular deep 6DOF pose estimation. So we want to investigate the 6DOF detection problem, and in specific, we want to investigate the problem that make the deep learning model suffer from different distribution on training. Like we have different configuration of the environment, and you have different cameras that are not available in the training set. And we're using synthetic data to train the deep network to overcome this problem. So as contribution, we evaluated specifically the domain randomization strategy to evaluate the impact of these strategies in the training of deep learning model. And we evaluated this in the 3D printed object scenarios that have a small and textureless object. And we investigate the model accuracy on real-world challenges like varying the illumination, the motion speed, and evaluate the model for different device segments. And we made available new dataset for 60OF post-estimation. So we make a tool to generate synthetic images for general purpose, and they make primarily the domain randomization process that have handle object size, colors, and handle texture and handle lights. And we put this in the image, and we have a real data set using to get annotations to validate the approach. So we have the images, the 3D box of the images of the object in the image, and the mask to put the object in handle records to use to train the detector. So we test these two different scenarios with different devices. So we use the Samsung Galaxy S8 and the Apple iPhone X, and we're testing the simple scenario with slow movement, one with motion speed increase, and scenarios with varying the illumination with and change the indoor illumination and turn off indoor light and uses only a small point light with handle movement. We use one detector proposed by Tekin to validate the approach, and we use it because it's the training adaptive and it's also available publicly. And we train configurations of training with real images, synthetic images, and we have configuration mixing the real and synthetic images, or making fine-tuning using only synthetic images and adjust the model with real images. And in the results, we show that the approach makes the synthetic and the real images can perform better than using only real images. And this is the same when you have a variational changes in the scenario, like motion and illumination changes, but also improve the results when you have different devices. And as a conclusion, we have evaluated the impact of DR with different strategies, and we evaluate how synthetic information can impact in the training of the dataset distribution and increase the model generalization to prevent the overfit. And training with real and synthetic data can simplify the annotation process to insert challenging without the need to annotate with real image. And we also made a new dataset available for a 3D printed object. It included challenges in motion, illumination, and device variation.
Thank you for the presentation, Kelvin. In the moment, we don't have any question, but I will start again. What is the size of this data set that you created in terms of synthetic and real data?
Okay, we have 20 million images for the real data, and we use it 4 million for synthetic, and we have to each scenario we have two I don't remember well, but is the size.
Okay, no problem, Kevin. Just to have an idea of the size of the data set, that is really important, since you will put it available for others. So that's for itself, it's a very nice contribution. So
we want to record more objects and scenarios in the future.
Guys, this is very nice, and not only this, but our work seems to be very interesting. So it's very interesting. Other question from myself is, what do you think that could be a very a contribution for this to the industry? Do you have in mind something?
Yeah, I think when we use synthetic data, we can reduce the amount of real data to train the model. So, and we evaluate in the work that fine-tuning can improve the model accuracy. In this scenario, you can think that you can train a model with synthetic data, and we use only a few amount of real data to perform adjustment in the model trained. So this decreases the time to train the models and to release applications on real scenarios.
Very nice. Gandhi Alma has a question here. What the data set did you use to estimate? What is the data set that you use to estimate?
Yeah, we use our own data set. We don't use any public data set because we want to evaluate some specific challenges that are not mapped yet in the other works, like when you change the device or when you have isolated the challenges. And we make a new data set and we make it public to our test too.
Okay, I think that we don't have any other question. So Gandhi is also asking you to send to him a link to the data set if it's possible.
Yeah, so, it's on the paper.
It's on the paper.
Yeah.
Thank you very much, Kevin, for your presentation. Congratulations for your work.
Thank you.
So I'll pass to the next speaker. That is Wilson Marcílio Jr., and the paper is From Explanation to Feature Selection, Assessing SHAP Values as Feature Selection Mechanism. So,
hi everyone, my name is Wilson. I'm here to present our work From Explanation to Feature Selection, Assessing SHAP Values as Feature Selection Mechanism. When working with high-dimensional data, we have the problem of the redundance among dimensions, which impairs existing techniques. And oftentimes we have to reduce the number of dimensions using dimensionality reduction techniques or feature selection techniques. When we are working with machine learning solution, we usually don't focus on the interpretable aspects of the preprocessing steps, such as feature selection. And the feature selections techniques show some explainability issues. For example, the filter maps methods do not leverage a model's characteristics for feature selection. The rapid methods choose a subset of only basing scoring performance, and the embedded methods have to be incorporated to each model being analyzed, which is an infeasible approach. So that our contribution is based on using SHAP values as a feature selection mechanism. The SHAP value is a model agnostic explainability approach that uncovers the feature contributions to a model's prediction. And we use the importance returned by the SHAP, which is a measure of contribution, to find the most important features and use them as feature selection. Okay. And comparing with well-known feature selection algorithms, we show that SHAP values present the best results according to a feature importance metric. Here's some background about SHAP values. The SHAP value is a model agnostic additive explainability approach in which a feature, a model's prediction is explained by the sum of contributions. We use SHAP values for compute the contribution of features for each class of the dataset in case of a classification problem, showing the first step. Then we use this matrix to compute the mean of each column, which is the mean of the contributions. And then we take the sum of these contributions and sort them according to the sum. Here, the features that most contribute will have the most importance for the model. We evaluated SHAP against 3 common feature selection approaches and according to classification and regression tasks using the XGBoost library. For evaluation, we use the keep absolute metric, in which we fix a number of features for classification and then mask the others. The mask is performed by taking the mean of the features and assigning the mean for each value of the features. Then we feed the matrix to the model and compute the scoring value. If we take this procedure with increasing number of features, we can have a curve like this. Here is the result for classification, in which we see the SHAP give the best results for all of the data sets. And the results for time execution show that SHAP is the only second worst technique for computing the results. In this work, we present a strategy for feature selection using SHAP values that address the problem of selecting features in the pre-processing steps according to interpretability issues. In future works, we plan to analyze the ordering imposed by the technique for feature selection to understand the critical parts of it.
Thank you, Marcílio, for the presentation. So for the moment, again, we don't have any question, but I will start with one. So, okay, do you select the features from the SHAP values, but using the performance of the objected the training model using these features? So yes. How expensive is that when you have a large number of features?
It depends on the method. If you are using SHAP values with any model, there's a technique to approximate SHAP values for any model called kernel SHAP that is pretty expensive. I think it's quadratic on the number of features. But if you are analyzing three algorithms, there are techniques that are fast. I think logarithm techniques to estimate SHAP values. So it depends on the type of the machine learning algorithm.
I see. Claudio Jung is asking a similar question as mine. Can you comment on the complexity visual of the chosen data sets?
I didn't understand. How come visual?
I think that you can see that. Can you comment the complexity of the chosen data sets that you make in your experiments?
Okay, I've chosen a mixed complexity. For example, we have the diabetes or the heart disease data set. There are data sets that have classes that are pretty separated. But for example, I choose one called immunese or Indian liver data set that have classes that are very mixed. So there are different types of complexity for the data sets. But for instance, for this paper, we focus only on the explanation size, not on the accuracy of the models. So it's isn't a matter we focus much on the data sets.
Mm-hmm. Okay. So my last question is, have you compared your technique to classical feature selection algorithms like the forward feature selection or the backward feature selection schemes?
No, I haven't. We only compare with ANOVA, multiple information in RFE, but the one you mentioned, we didn't compare.
Yeah, these two are classical feature selection techniques in the literature of data mining, in which you select one variable and see what's happening. You put in the model one variable at a time, then you put two variables at a time and see. This is the forward feature selection. The backwards, and you are removing from all the features one by one and see what is the better choice. So maybe a suggestion to complete your work doing a comparison with these two greedy strategies for feature selection, for example. Okay, thank you very much for the presentation. Thank you very much for the audience of this last technical section of CBGRAPI. So next we'll have the talk, the invited speaker Olga at 5 o'clock, and then we'll have next the closing section. So see you there. Thank you very much. I hope to see everyone in CBGRAPI next year, also at Gramado, that we choose yesterday at our plenary section. Thank you very much. Bye-bye. Take care.